Welcome to the video for Lecture 13. This video is about control systems. In this video, we will talk about open-loop control system, closed-loop control system, stability, control modes, and control mode transfer functions. Open-loop control systems do not have a connection between a process output and any of the process inputs. They are generally stable, but they do not adjust to changing external disturbances, inputs, or loads. Closed-loop control systems have a connection between a process output and one or more process inputs. They adjust inputs in response to changes in process outputs due to either set point changes or changes in external disturbances, inputs, or loads. Closed-loop control systems need stability analysis. In a process control context, error is the difference between the measured process output and the desired process reference input, which is also called a set point. The controller uses the error, ES, as the input to produce a process adjustment or controller output signal, PS. The process adjustment depends on the control mode and control coefficient settings. The selection of the control mode and control coefficients affects process stability. Stability indicates that the transient process response or output remains within some acceptable range. An unstable process generates output that becomes uncontrolled under certain circumstances. Open-loop processes are generally stable. Stability of closed-loop process is an important issue. Under certain circumstances, the process output can oscillate at either increasing or constant amplitude or a decreasing rate. The final value theorem can be used to estimate long-term process stability, but it does not assess the overall process output shortly after set point or load changes. Many control systems describe processes with multiple process and control components. The following diagram shows a typical closed-loop control system. Controller is within the red circle shown here, which is right after the error input and before the actuator. It is the process decision maker. So, what is the basis for a decision mode? Well, controllers use the error signal to generate control signal that is used to adjust the actuator. There are a total of 6 basic control modes used in industry in closed-loop control signals. They are two-position or on-off control mode, proportional, integral, or the combination of proportional and integral, or the combination of proportional and derivative, and finally the PID control, which is proportional plus integral plus derivative control. With the most common on-off control, the controller output signal is either fully on or completely off. On-off control is commonly used in thermostats for controlling heaters and cooling fans or air conditioners. The on-off functions above are not practical, though. They lead to excessive equipment cycling on and off. Theoretically, the heating equipment would turn off if the measured temperature is, say, just 0.001 degrees centigrade greater than the set point, and it would turn on if similarly the measured temperature is only 0.001 degree less than the set point temperature. Rapid cycling is undesirable because turning motors on and off rapidly is hard on the motors and wastes energy. Cycling is reduced by adding a switching differential or deadband. In a thermostat with a switching differential or deadband D, for example 2 degrees, the heater does not change its on and off status unless the difference is bigger than the 2 degrees set up. For example, a graph shown here is the deadband, which is between P2 and P1, and the system only turns on if the azure is bigger than D, and system will turn off if the azure is smaller than 0. Similarly, deadband application also is used in two-position cooling control system, which is shown here. Again, the deadband D is set to be an acceptable range where the system will turn on if ET is smaller than -D, and it will turn off if ET is bigger than 0. And the deadband D is the difference between when P1 occurs and P2 occurs. When the heater is off, the water temperature will decrease gradually to be smaller than the required value R. Here is the example heater response. However, the heater won't turn on immediately when water temperature drops because of the deadband application. Instead, it turns on when the water temperature is smaller than R minus D, where D is the deadband. When the heater is on, water temperature starts to increase. The heater will turn on once the water temperature becomes the required. It will turn off once the water temperature becomes the required value. So in the cooling fan or air conditioner controlling system, when the cooling fan or air conditioner is on and the temperature is decreasing, the cooling fan or air conditioner turns off when B is smaller than the required temperature, or in terms of azure, ET bigger than 0. When the cooling fan is off and the temperature is increasing, the cooling fan turns on when B is bigger than R plus D, or in terms of azure, which is ET is smaller than minus D. The air-conditioned room fluctuates between the set point temperature and the set point plus the switching differential. So the deadband or switching differential observations are temperature difference between when a thermostat turns a device on and when it turns a device off. Almost always we have some azure, which is the difference between the set point and the measured temperature. And some overshoot might be possible, depends on sampling rate. Increased deadband will increase output variation and reduce cycling. And decreased deadband decrease output variation and increase cycling. Some deadband is desirable to prevent rapid cycling. Incremental on-off is an alternative to fully on-off control, where precise control is not needed. Incremental control is sometimes used to control ventilation doors or naturally ventilated buildings. In these cases, doors are open to cool the building by letting interior hot moisture air to exhaust from the building and cool dry outdoor air to enter. If the interior air temperature is above the set point, the doors are opened further in an increment, maybe an inch or two. If the interior air temperature is below the set point temperature, the doors close in increments. Since natural ventilation of a large space using doors like these is usually a slow process, the controller typically waits a few minutes before taking another interior temperature measurement. The delay between readings keeps the system from adjusting the doors to open too often. A switching differential can be used also to reduce rapid cycling. Over time, the doors open and close around the opening size needed to control the indoor air temperature. This is the end of introduction to Azure, open loop, and the on-off system. So in the next video, we are going to talk about PID controls.